I'm Jason Toschlog from Flexware Innovation. I'm CTO of Flexware and help out our product development teams that are focused on providing software for production analytics. Today I'm going to talk a little bit about bottleneck analysis. It can be a complex topic. I'm just going to cover the overview key points. Okay, so for bottleneck analysis, what are we trying to solve with it? So the name implies that the bottleneck is a restriction of flow, and we have restrictions of flow of materials inside of manufacturing facilities, and understanding those restrictions is key to improving the ultimate throughput of your production process. So there's really several vantage points to think about with bottleneck analysis. First of all, when you design a manufacturing line, you've designed in some concept of what the bottleneck is or what the pacemaker might be within that production process. So let's start there. If you take a typical manufacturing process, let's break this up into multiple operations. Let's just say that we have an operation 10, an operation 20, an operation 30, and an operation 40. So for your industry, these operations would be the changes we're making to the product as we produce it. So if you're in a packaging operation, this might be a labeler, a cartoner, a case packer. If you're in the aluminum can manufacturer, this could be your cupper, your body makers, your washers. These operations are generic in this form, but can apply to a lot of different industries. So if we look at these various operations that we need to apply, typically, when you're designing a line, somebody has given you some type of target for production throughput. So let's draw that line on here. Let's say that we're being asked to produce 1,500 parts per minute. So parts per minute. So as a manufacturing engineer, I'm looking at this and saying, okay, what machines am I going to procure or deploy at each of these operations in order to reach that goal? And I need to have some excess capacity there to account for downtime or changeover or tool changes, etc. So let's add a scale here on the side. So we can say we've got 500 parts per minute, 1,000 parts per minute. So this would be our 1,500 parts per minute and 2,000 parts per minute. So typically when we build these lines, we work with OEM equipment manufacturers, and the machines that they provide come to us with a maximum rate, a rated speed, a theoretical run rate, something like that. So we have to take that into consideration when we're designing our line. Again, we also have to add in extra capacity to cover all the non-production time. So let's do some examples here. So let's say that operation 10, that the standard piece of equipment that we can buy does 1,000 units per minute. So we buy machine number 1, just call that M1. And that's obviously not enough to reach our goal of 1,500 parts per minute. So we buy a second one of those machines, which that brings us up to the 2,000 mark. Now we're at that rate, and we've got roughly 500 parts per minute of excess capacity that we can exceed our goal. Now let's look at the operation 20. We'll say this is a more complex operation. The machines here are not as fast. We're going to need even more of them. So let's say that we have roughly 300 parts per minute. So we have to buy quite a few of these machines. So let's just keep going here. Okay, so we're at 300, 600, 900, 1,200, 1,500. That's right at the limit. It's probably not safe to have just that amount, so we would probably have an extra machine here that does the 300. So machine 1 here again did 1,000. Machine 2 did 1,000. So let's start summing these up as we go. So we've got a total of 2,000 parts per minute on operation 20, and we have now 1,800 parts per minute on operation 20. Let's say that operation 30 is a very fast process and one machine does more than enough of our capacity. Let's say that it provides 3,000 parts per minute. And then op 40, let's just do something where we've got 2 machines here. Let's say that that's 1,000 again. And this is our extra 1,000. Okay, so now we've purchased equipment that each of the operations can exceed what our goal was. And if we round out our sum of our capacity at each one of these, we can see that operation 20 is our designed-in bottleneck. It's our pacemaker. It's our slowest process. Even with all these machines, the maximum throughput for this line is going to be the 1,800 pieces per minute because of this bottleneck. So we can draw kind of a threshold. Okay, and so this is our capacity. Okay, now some people might call that your maximum capacity. In reality, you could, for short stints of time, you could produce more than the 1,800. So for example, if this is our last operation at 200 parts per minute, we had a huge queue of parts here. For short stints, we can produce at 2,000 units per minute. But over the period of a production shift, your capacity is your average maximum capacity that we're ultimately going for. So if we look at the difference between what our theoretical best capacity is versus what the target production rate was, that difference is our allowable OEE difference, right? So if your OEE is less than 100%, which it is in almost all cases, you're not going to be producing at full capacity. You're going to be at somewhat less. And so typically you want to make sure that you've got enough capacity going in that if you're running at 80 or 90, whatever makes sense for you and your business, that you still have that capacity to be able to hit our target production goal. You want there to be some safety there. Okay, so this is kind of phase 1 of bottleneck analysis, is just making sure that our equipment itself has the capacity to produce. The next step is, and we're going to make an assumption here. We started out talking about aluminum can manufacturers or high-speed packaging. We're going to assume that this is a high-speed manufacturing line with conveyors that connect each of the machines. So the next thing we have to think about is how much inventory do we need to store or have in between each of these operations in order to account for momentary stops that are a natural part of the solution. And so the things you have to consider here, there are planned downtime events. So if you're a 24/7 operation, you're doing planned downtime activities in potentially working shifts. You've got to account for that. If you have tooling that wears out over time, you have to replace that tooling. There's a tool change time. If you have multiple products, there's a changeover for those products. You have to account for that. And you need to understand how long each of those things take in order to create this buffer of inventory between each of the operations. So let's denote that here. So before we come into operation 10, the type of inventory that we're trying to monitor is our raw materials. It's whatever these machines are going to consume in order to provide the line. So a lot of times we denote inventory with a triangle. So I'll just put it here. I'll put an R M in this for raw material. And then we're starting to produce work in process material as we go through. So between operation 10 and operation 20, we're going to have some WIP, work in process. Same between the next two operations. Same between the next two operations. And finally, when we're done with operation 40, we should have a finished good. So you have finished good inventory here as well. Okay, so some things we need to think about here is how much inventory do we need in between there, and what would be our limits, and what would we be actually aiming for? So a lot of times we'll indicate this with a bar that says, what is the level of inventory that I have inside of this raw material storage space on my line, and that there'll be some kind of a low limit and some kind of a high limit that we're trying to monitor. Having this queue completely full is not necessarily good. Having it completely empty is not good, but it is different at different stages. For this first raw materials side, there is no risk of blocking, so there really isn't necessarily a high limit there, but we do care about the low side of it. If we run out of raw material, I can't produce. I'm starved to be able to run. As we move down the line, we actually have a high and low for each one of these. And finally, for our finished goods, we actually have a high limit here. If we fill up this finished goods queue, we're blocked, we can't produce anymore. We don't necessarily have a low. If we're low on finished goods, it's not going to stop our process from actually running. So each of these inventory levels need to be sized based on typical outages within the process that allows the rest of the machines or operations to continue to flow. That calculation can be complex, and it is an important part of bottleneck analysis, but it's also a big part of designing the line to flow properly. Okay, one thing on inventory is just to say, well, what are we aiming for? A number of parts or units, or is it time? Typically people like to understand both. You have to size your conveyor or your queues for a number of parts, but you also ultimately want to relate that back to minutes. So it's how many minutes of downtime can I have on one of my operations without blocking or starving, another operation in the process. And so each one of these will be sized according to those needs. So we can just depict, the current status. Let's say we've got our current inventory level. Our raw material is at a healthy state. The work in process between operation 20 is in some healthy state. Let's say that this operation 20 has been down for a few minutes. Maybe its inventory is somewhere in the low area. So we want to be able to monitor that. And we'll go ahead and just show the rest of these as being in a healthy state. So as we start to think about bottleneck analysis, what you're looking for is problems in this plan. So we've completed the plan. Now let's think about what could go wrong. So the easiest thing to look at for bottleneck analysis is the actual run rate of the individual machines. So for example, if one of these operation 20 machines is actually running at 150 parts per minute instead of 300. And we could do this for various reasons. The operator adjusts the machine speed because he's dealing with a problem with jams on the conveyor or whatnot. You could also have one of these that was just down for unplanned downtime. But as that number drops, especially for your bottleneck, the capacity of your line goes down by that amount. So we've lost from 1,800, we've lost 150 on our capacity, and we cannot produce more than that throughout the shift. So focusing in on your bottleneck or your constraint in the line is a typical thing that people do. They manage to that, and they look upstream and downstream from that. So let's do another scenario here where, in this case, our inventory is low here. It drops to 0. This particular machine is starved, has no parts to run. Because it is the fastest machine in our process, that may not be a problem. It might be able to recover. That's why we focus on the pacemaker or the bottleneck as being the primary focus area. Now, what if the pacemaker here, or the bottleneck, by plan, is actually starved? That means that something else is causing it to have a problem. So let's take that scenario here where, okay, our inventory between operation 10 and 20 has reached basically a zero state or a low state, and it's starving the machines here of parts to be able to produce. So in that case, to understand the root cause of our downtime or our inefficiency, we have to look upstream and say, well, what is causing the problem here? It could be that one of these two machines is in a standby state. It could be starved of raw material, so it could be a raw material problem, or it could be that one of these machines is under a changeover or a downtime event. So the assignable cause for why our process is not performing at capacity is upstream from the process. It could be the opposite. It could be that the queues are at the high levels of some of these future operations, and they're blocking us. So we can't produce any more product because our conveyors are full. In that case, we have to look upstream to find the actual problem within the process. So let's talk about the more complex scenarios here. The more complex scenarios are that it's combinations of all of these things. It could be that you've got certain machines that are dialed back, not running at full speed. You have some downtime, you have some changeover. To be able to figure out where your real problem is critical. So first of all, let's talk about why do we even care? First thing is you want to understand the root cause of these performance problems so that you can make adjustments. Maybe these queue sizes need to increase. Maybe we need an extra machine. Maybe we need to schedule our changeovers differently. All of those things, you need to understand which things are causing you to not meet your capacity. The second reason why we care about this is if you've got multiple problems, multiple reasons the line is down, you need to prioritize which one you fix. Typically, you're looking at your pacemaker, your bottleneck, and you're saying, I got to fix that first, and I work out from there. So those are all reasons why we ultimately care. Another reason, I guess, is that, just to support valid production planning, if through the dynamics of running our process, we can't realistically hit that 1,500 parts per minute, then it doesn't do us any good from a production scheduling perspective to assume that we're going to be able to do it. So you need to understand what's real about your process and what you can and cannot do. Okay, so finally, let's talk about things talk about how do you actually do this in the real world. So obviously at Flexware, we provide technology solutions to collect a lot of this data and to monitor it. So what are the things we can monitor? So we can monitor the machine state. Every one of these machines, we can say whether they're running or not running, whether they're blocked or starved, or what we call standby mode. We can tell if they're running slowly because we can look at what the machine's current rate is set at. So we can monitor all of that. So this first level of understanding where's the bottleneck is relatively easy to find. The second one, when we look at these inventory levels, this is typically imperfect data. It's usually an estimate. We usually have sensors that tell us the counts of parts coming into a machine and leaving the machine, and we can assume that if we look at that over time, we can roughly estimate that, but we don't have perfect information. If people come and remove parts from the line, we can't see it. We don't know if they did a full line clearance and reset it to zero before they change parts. So we always have to assume that our visibility into this inventory is limited. What we have found is that there are ways to get very precise counts, and we do that at critical steps in the operation. But some of these sensors are expensive, so we're always going to have limitations there. The next piece of information that we like to use that we can leverage is that really, if you don't have this inventory information, the best predictor of that is how have I generally been running? How many parts per minute have I actually produced on each of these operations over a period of time? And that time window is what's critical. That time window has to cover the inventory time support that we have. So let's say that it makes sense that I want to look at what's the average throughput of operation 20 over the last 15 minutes. And if I compare that to all the other machines, whatever my average throughput is, my lowest average throughput is on each operation, that tells me what my current bottleneck is. And that can change over time. So what we found is that, obviously looking at that over a production shift tells you historically what was my bottleneck over that production shift. And it directly relates to what I was meant to try to produce. But you can also look at it at different time frames throughout the operation to get more of a real-time view of this. But when you have multiple factors like slow running speed, some downtime, and all these things coming to tease that out of the data can be complex and difficult to do. Okay, so I covered a lot of topics today. This can be a very complex topic. I tried to hit just the highlights for you guys, but contact Flexware if you have any questions. Thank you.